coming to the problem. So this is a portal frame that has been given. So for this frame, we are going to analyze by using a slope deflection method. Finally, you're going to sketch all the figures, that is elastic curve, bending moment, and shear force diagram. So when we see this problem, so here AB, it is having a UDL of 20 kilonewton per meter, and BC portion is an overhang portion, so which is having a point load at the free end. And again, BE, it is having a lateral load acting onto this member. So that is horizontal load 20 kilonewton. So as this load is acting at horizontal load is acting in the BE member, so the member is going to have a sway. But at the end support, it is a fixed support. Therefore, it is restraining the structure, uh, not moving. So that is the reason here there will be no sway. So, and here in this case also, there is a no lateral load acting in this direction towards right side. So there is a no sway in this case also for this, the other side of the frame. So here in this side, as you are having a lateral load also, but here the A support is getting restrained. So here the sway condition has been avoided. I mean, sway condition is not there. So first step, we are going to determine the degree of the freedom. So as the support A is a fixed support, therefore there is no rotation and there is no translation. And coming to this B support, so there is a translation, sorry, there is a rotation, but there is no translation. Again, at the E support, there is no rotation and there is no translation. Since A and E are fixed supports, there will be no theta and no delta. Whereas at the B support, there will be theta, but there won't be any delta. So now the degree of freedom is 1. Therefore, the theta B is your unknown. Now coming to your next step, that is calculation of your fixed strain moments. So we are considering first for span AB. So I am drawing span AB. So it is having a UDL of 20 kilonewton per meter. So which is of 4 meters and 2i moment of inertia. So this is A and this is B. So AB, you are having at A support and at B support, these are the fixed strain moments, directions. So which is having double L square by 12 and double L square by 12. So here, as it is in anti-clockwise direction, it is negative sign convention. At B end, it is clockwise, therefore it is positive. So therefore, I am writing MFAB will be equal to minus WL square by 12. So that is minus 20 into 4 square by 12. So therefore, it is minus 26.67 kilonewton meter. Similarly, MFBA will be equal to plus WL square by 12. So that is plus 20 into 4 square by 12. So that is 26.67 kilonewton meter. Now considering a span BC, so as it is something like a cantilever overhang portion, so which is of 10 kilonewton. So this is B and C. So this is 2 meters and 2i. Therefore at B it is having a hogging moment of 10 into 2, that is WL. Therefore MFBC will be equal to minus 20 kilonewton meter. Next step, for span BE. So if you consider the BE span, so this is B support and this is E support. So here at the point center, you're having a lateral load acting, that is 20 kilonewton. So this is 2 meters and this is 2 meters. So this is I. So as the load is acting in this direction, so at ends B and E are going to have resist the moments in this direction. So these moments, so these are WL by 8 and this is also WL by 8. So since this is in anti-clockwise direction, it is negative and this is clockwise direction, therefore it is positive. Now I am calculating MFBE moment will be equal to minus WL by 8, that is minus 20 into 4 by 8, that is minus 10 kilonewton meter. Similarly, MFEB will be equal to plus WL by 8 because clockwise direction. Therefore, 20 into 4 by 8. So that is plus 10 kilonewton meter. So these are the fixed end moments we calculated for all the members in a portal frame. So now using these fixed end moments, you are going to substitute in the slope deflection equations. So in the next step, we are going to use the slope deflection equations. So generalized slope deflection equation for MAB is the fixed end moment MFAB plus 2EI by L into 2 theta A plus theta B, that is moment due to the rotation, and minus 6EI delta by L square, that is moment due to the settlement. But here in this case, as there is a no sway condition, therefore this delta will be equal to 0. Similar way, we are going to write for the equation for a BA span also. So here also delta equal to 0. Therefore, now the slope deflection equation is going to become MAB will be equal to MFAB plus 2A by L into 2 theta A plus theta B, and MBA will be equal to MFBA plus 2A by L into 2 theta B plus theta A. So here you can write this settlement can be a sway also in this a condition as it is a frame. Now coming to your next, we are going to substitute all the values like fixed end moments and rotations in this problem, in this equations, and we are going to solve. So here in this, as A is a fixed support, so theta A will be equal to 0 and I is a 2I moment of inertia. Therefore, the simplified equation for MAB will be this one. And similarly for MBA also, you are going to substitute theta A will be 0. Then the finalized equation will be this one. Similarly for MFBC, as we already calculated, so here we are having a hogging moment of minus 20 kilonewton meter. So that is a MFBC. So next again, we are going to take us for MBE. So MBE also, as E is a fixed support, theta E will be equal to 0. Therefore, now the equation is going to become like this for MBE case. Similarly, for MEB, again you are going to substitute theta E as 0. Then the final equation will become like this. After substituting all these values and getting the finalized equation for your end moments, then in the step 4, you are going to use the equilibrium equations. So for this frame, as you are having only one joint, that is your B joint. So therefore here it will be equal to sigma MB will be equal to 0. So that means MBA moment plus MBC moment plus MBE moment should be equal to 0. So we are going to take this. So MBA plus MBC plus MBE will be equal to 0. So as we already calculated MBA value, this is an MBA equation, and MBC is minus 20, we already know. And MBE is this minus 10 plus EI into theta B. So finally you got the theta B value as 1.11 by EI. So which is in the positive direction we are getting. Therefore it is a clockwise rotation. So now, after getting this theta B, then you're going to draw the elastic curve for this theta B. So since theta B is clockwise, so it will be in this direction. Here also. So when we draw a tangent, so like this. So here theta B will be equal to 1.11 by EI. So which is in the clockwise direction. So this is B, this is C, and this is E portion. So this is how you are going to draw your elastic curve. Next, calculation of your final end moments. So by substituting theta B value in all these following equations, MAB, you are getting it as minus 25.56 kilonewton meter. MBA is 28.89 kilonewton meter. MBC is minus 20. MBE is minus 8.89 and MEB is 10.55 kilonewton meter. Now, when you add all these values, you're going to get a zero momentum. So now after calculating the final end moments, these are the final end moments. Now you're going to draw your Benny moment diagram. So first we'll draw the free body diagram. So this is A, B, C and E. So we'll draw the external loading also 20 kilonewton, 2 meter, 2 meter. And this is a point load of 10 kilonewton. So which is of 2 meter. And here it is a UDL of 20 kilonewton per meter. So MBA is negative you are getting. So it is anti-clockwise direction of 25.56 kilonewton meter. MBA you are getting positive, so clockwise. So this is 28.89 kilonewton meter. MBC again it is a negative of 20 kilonewton. And MBE is negative. Therefore, it is anti-clockwise direction of 8.89 kilonewton meter. And MEB is positive. Therefore, again, it is of clockwise direction of 10.55 kilonewton meter. So now for this, drawing a Benny moment diagram. Okay. So this is AB, E and C. So first we'll draw the simple Benny moment diagram. So for simple Benny moment diagram, so here it is 20 into the span here is 4 meters. So 20 WL square by 8. So this is, so WL square by 8 is 20 into 4 square by 8. So that means this will be equal to 40 kilonewton. And here it is a cantilever. Therefore, it is having a hogging moment of 20 kilonewton meter. So this is 20 kilonewton meter. This is negative. This is positive. Again, for this, again, you're having, as this is a simply supported beam. So here also it is a point load we are having. So which is of positive. So WL by 4, that is 20 into 4 by 4. So that will be 20 kilonewton meter. So this is all the simple Benny moment diagram. Now coming to this end moments. So which are in hogging in nature. So we'll draw the hogging value. So this is 25 and this is 28. Just a minute, I will draw. So this is 25 and this is 28. So by joining these two, here having 28.89 kilonewton meter and this is 40 kilonewton meter, 25.56 kilonewton meter. So for this BE span, as this is in the hogging in nature, so now we are going to draw, this is 8 and this is 10. So this is negative and this is also negative. So this is 8.89 kilonewton meter and this is 10.55 kilonewton meter. So now the shaded portion will be your resultant bending moment diagram. So here once again we'll see So AB, first due to the UDL, we just draw the simple bending moment diagram, that is WL square by 8. So this is WL square by 8. So that is 20 into 4 square by 8, as we are treating it as a free bending moment diagram. And due to this end moments, we got a hogging moment. So the intersection of these two is going to be the resultant bending moment diagram for AB span. Similarly, for BC span, as you are having only a hogging moment of 20 kilonewton meter, so that 20 kilonewton meter will be in this direction. And next, due to this BE, so BE again you are having a point load at this point. So due to this one, the free bending moment diagram will be WL by 4, that is 20 into 4 by 4, that is 20 kilonewton meter. And again you are having a hogging moments 8.89 and 10.55 at each end, B and E respectively. So the intersection of these two will be a resultant bending moment diagram. So this will be your final bending moment diagram for this figure. Now, coming to the next one, shear force diagram. So for same, the shear force diagram, we are going to calculate the first reactions. So for that, you are going to draw the free body diagram. So AB, you are having a UDL of 20 kilonewton per meter. So which is of 4 meters. And BC, you are having a point load. And again, this BE member, you are having a 20 kilonewton per meter, which is 2 meters and 2 meters. This is also 2 meters. So now AB, it is anti-clockwise direction, negative, and BA positive, which is of clockwise direction, and BC again anti-clockwise direction, negative, and BE anti-clockwise as it is negative, and EB also positive, therefore it is clockwise in direction. So for this free body diagram, you're going to find the reactions first. So I'm making this as RA and this reaction to be RB1 and this reaction to be RB2, and now these reaction to be RB3 and this reaction to be RE. So now considering AB span, now moment about this portion. So sigma MA will be equal to minus 25.56 kilonewton meter. That is summation of the moments at this point will be hogging in nature, therefore minus 25.56. Now RB1 into this 4 minus 28.89 moment at this B minus 20 into 4 into 4 by 2. So that is UDL moment. So that will be equal to minus 25.56. So by solving this, you are going to get RB1 will be equal to 40.83 kilonewton. Now, RA plus RB1 will be equal to 20 into 4, that is 80 kilonewton. Therefore, RA will be equal to 39.16 kilonewton. So this is your RA reaction and this is your RB1 reaction for AB span. Now consider BC span. So RB2 will be equal to 10 kilonewton. So that is for BC span. Now consider BE span. So now consider your BE span. So considering that, I am taking moment about I am taking moment about E. So therefore, moment about E will be equal to, okay, from this direction, from here, I am seeing like this. So moment about E will be equal to minus 10.55 kilonewton meter. Therefore, RB3 into 4 minus 8.89 minus 20 into 2 will be equal to minus 10.55. Therefore, RB3 will be equal to 9.58 kilonewton. Therefore, RB3 plus RE will be equal to 20 kilonewton and RE will be equal to 10.42 kilonewton. So these are the reactions we are getting by taking the moment about these points. Okay. So after getting the reactions, you are going to draw the shear force diagram. So these all are the reactions. Just I'm going to place all these things here. So this is 20 kilonewton. This is 20 kilonewton per meter. And this is 10 kilonewton. Just I'll write the reactions only. So here RA is equal to 39.16 kilonewton and RB1 will be equal to 40.83 kilonewton and this is 10 kilonewton. And here it will be equal to 9.58 kilonewton and RE will be equal to 10.42 kilonewton. So for this, the shear force diagram will be okay. So for this, it is 39.16. 39.16 and here it will be, so this is 39.16 kilonewton since it is positive shear and this is anti-clockwise negative shear. So this is 40.83 kilonewton. And similarly here also it is of clockwise shear which is of 10. Therefore, here entire thing is positive 10 kilonewton and 10 kilonewton. So this is A, B, C and this is E. So now coming over here. So here it is again a positive shear. So which is of some 9.58. And again at this portion again it is of anti-clockwise. So negative shear. So this is negative and this is positive. So this value is 10.42 kilonewton. So this is D point. So this is 40.83 kilonewton and this one is 9.58 kilonewton. So this is your shear force diagram. Okay. So once again, so as it is like a simply supported beam UDL. So it is like a linearly varying. So the reaction here is 39 and here it is 40.83. So at A it is in positive shear and at B it is in anti-clockwise direction. Therefore it is negative shear. Whereas in the BC span, it is in the clockwise shear only. I mean positive. So it is whole thing is positive. Whereas coming to here BE, so at this B point, it is in clockwise shear positive. At E point, it is in anti-clockwise. So it is in the negative value. So this is the final shear force diagram. These are the references. Thank you.